This week, we will be taking a look at data integrity issues. The management of data is driven by two goals: making data available and maintaining integrity of data. Availability means making the data available to whomever needs it, whenever they need it, and whatever form individuals might need that data in. The integrity of data, on the other hand, implies three goals. The first goal is protecting the existence of data. This means that data are made available when needed. There are many ways to achieve this goal. It can be preventative, that is, isolating the data through backups. And the second is remedial, performing database backups and recoveries. The second goal is maintaining the quality of data. This means that making sure that the data are accurate, complete, and current. The third goal is ensuring the confidentiality of data. This means that data are accessed only by those who are authorized to do so, and data access control processes are kept in place, and encryption systems are put together so that individuals can only access that data that they are supposed to. There are three broad strategies for data integrity. Legal strategies are externally imposed, and they consist of laws, rules, and regulations. Privacy laws may be an example of ensuring data integrity. The second strategy for ensuring data integrity is administrative. Administrative strategies are organizational policies and procedures. For example, standard operating procedures for storing all backup files in a locked vault may be an example. Us, as individuals, pay a lot of attention to legal strategies for ensuring data integrity. We are concerned about, for instance, whether Congress or the Senate has passed any laws that ensure the confidentiality of our information. We are less likely to pay attention to administrative policies of organizations. The third strategy for data integrity are technical strategies. Technical strategies are those that are incorporated into the computer system. For example, database management systems, application programs, or operating systems may have technical constraints imposed on them to ensure data integrity. The referential integrity constraint in most database management systems is one such technical approach to ensuring data integrity. Our focus is on data stored in multi-user computer databases and technical and administrative strategies for maintaining integrity in computer system environments. This is commonly referred to as database integrity. Transaction management focuses on ensuring that transactions are correctly recorded in the database. The transaction manager is the element of a database management system that processes transactions. A transaction is a series of actions to be taken on the database, such that they must be entirely completed or entirely aborted. A transaction can be thought of as a logical unit of work. Transaction managers are designed to accomplish the ACID: atomicity, consistency, isolation, and durability concept. Atomicity: if a transaction has two or more discrete pieces of information, either all of the pieces are committed or none are. This refers to the goal of the transaction manager to ensure that the entire transaction gets processed and accomplished. Consistency refers to making sure a transaction either creates a valid new database state, or if any failure occurs, the transaction manager returns the database to its prior state. Isolation refers to the transaction manager making sure a transaction in process and not yet committed remains isolated from other transactions that are being processed. Durability refers to making sure that the committed data are saved by the database management system in case of a failure and a subsequent system recovery. When updating a database, most applications implicitly assume that their actions do not interfere with the actions of others that are also using the system. If the database management system is a single user system, then one can be fairly certain that this lack of interference is guaranteed. Most database management systems, however, cannot provide that guarantee. Most database systems are multi-user systems where many analysts, many applications can be accessing a database at the same time. When two or more transactions are allowed to update a database concurrently, the integrity of the database is threatened. Uncontrolled concurrent updates can result in a lost update or even a phantom record problem. To prevent lost updates and inconsistent retrieval of result sets, the database management system must incorporate a resource lock. A resource lock is a very basic tool of transaction management to ensure correct transaction behavior. Any data retrieved by one application with the intent of updating must be locked out or denied access by other applications until the update is completed or aborted. In the example below, we have two users, user A and user B. Both users are trying to modify a record in the database. The modification of the record takes place sequentially and relies on previous states of that record. The result is an inconsistent transaction or data being lost. To avoid the lost data problem, what transaction managers and database management systems can do is deny access to records that are being read by other users. In this case, the record is denied to user B who is attempting to access that information. This record can only be accessed after user A has released the transaction lock. Resource locking or record locking may solve some data and retrieval integrity problems, but it may lead to other problems, sometimes referred to as a deadlock or deathly embrace. In this case, suppose user A and user B were actually accessing two records, record 1 and record 2. First user, after locking one record, might need to read record 2 for an update, and user 2 might want to read record 1 for an update. In this case, both records being locked due to prior attempts might result in deathly embrace or deadlock. The state of a database can change as transactions are processed. In order to recover from data loss or damage, it is necessary to ensure backup data or a complete copy of the database or necessary data to restore the accuracy of a database. Preferably, backup data should be stored on another medium and kept separate from the primary database. Data stored for backup and recovery are generally some combination of periodic database backups, transaction logs, and before and after image logs. Recovery strategies use different combinations of backup data to recover a database. Here is a potential backup procedure of a database management system. You will see that the server, as the first state, wishes to perform an update transaction. This update transaction needs to be logged. Subsequently, the record is obtained from the database management system for that transaction. After the record is retrieved, an image of the record is made to make sure that we know what the data looks like before the change. Then the record is processed based on the transaction parameters and the record is updated in the database management system. A log is recorded after the update to make sure we know what the database management system looks like after the transaction has been processed. The results of these transactions are conveyed back to the server, and subsequently the database management system can be periodically backed up. There are a variety of failures that might occur during a transaction, including programmatic errors, actions by the transaction managers, maybe even a self-abort or a system failure. The type of recovery strategy or procedure used in a given situation depends on the nature of the data loss and the type of backup data available and the sophistication of the database management system's recovery facilities. One could easily switch to a duplicate database. This is the technology approach advocated by RAID. Another option is to perform a backup recovery or a rollback, and this would mean returning the database management system or the database to a prior state by applying all the before images that have been taken. One could also perform a forward recovery or a roll forward. A roll forward is to apply the after images to a prior backup and reprocess all transactions that were committed prior to the failure. The second integrity goal is to maintain data quality, which typically means keeping data accurate, complete, and current. Poor quality data have several detrimental effects. In fact, poor quality data may impact customer service when there is a dissatisfaction with poor and inaccurate information or lack of appropriate information. High data quality can be ensured by imposing constraints on the integrity of data. These constraints can take a variety of different forms, ranging from type, size, values, range, and many, many more. Type, for instance, means that making sure the data item is of actually a specific data type. For instance, ensuring that the data type is in fact numeric, or if it is integer, it is in fact integer and not of another data type. Size, making sure that the data item does fall within a minimum and a maximum range or size of the data item. One important aspect of data integrity is ensuring that the data is secure. There are two processes that are very important to ensure data integrity and the security of data. The first one is that of authentication, and the second one is that of authorization. The following model is a general model of data security. You will notice both the authentication and authorization processes depicted here. In this case, on the left-hand side, you see the user, and the user requires access to a database. And so we have a user ID that is entered by the user in addition to a password. This user ID and password combination is checked against authentication tables. These authentication tables keep track of users and whether they have access to the database system. If a user's database access is denied, they are returned back to the login screen. If, on the other hand, the user is granted access to the database system, one needs to make sure that the user can access only that data that he is authorized to. This is an authorization check, and this is based on the retrieval request of the user. If the request is denied, the user is informed that they are denied. Otherwise, the data is retrieved from the database and the results are sent back. Both authentication and authorization are performed based on role and authorization tables in the database. There are a variety of different authentication mechanisms based on information remembered by the person, objects possessed by the person, or other personal characteristics. Here is an example authorization table where the authority of each user or group is depicted. In fact, the MySQL database that we have all been accessing over this semester does have authorization tables, and what is listed in those tables is the databases that you might have access to in the MySQL server. SQL authorization is based on grant and revoke privileges. When your accounts were being created, I was using grant and I was granting privileges on certain tables, on certain entities, on certain databases to each individual user. At the end of the semester, or maybe even next year, I might revoke these privileges. Again, this is based on how routine maintenance is on these servers. A firewall is another way to ensure data integrity and to protect the database. A firewall is a device placed between an organization's network and the internet. And the firewall monitors and controls the traffic between the internet and the intranet or the organizational network. Uh, a firewall can be configured to do many things. Specifically, it can restrict access to specific applications, so database requests from outside the organization's intranet would not be allowed into the organization via the firewall. Another approach could be to restrict packets to those with designated IP addresses. Encryption is another way to ensure data integrity. Encryption is really as old as writing and is associated with the earliest ciphers. Sensitive information needs to remain secure, and one way to ensure that security is to make sure that the text or the information that is being transmitted cannot be understood by people who try to access it um, other than the individual who is supposed to receive that information. Encryption actually hides the meaning of the message. It does not hide the information itself, but it hides the meaning of that information. And decryption actually reveals the meaning of the encrypted message. Public key encryption is really the way encryption is performed on the internet, on the World Wide Web. In public key encryption, there are actually two keys. There is a key known as the public key, and there is a private key. When we want to encrypt something to be received by another individual, we will use the receiver's public key to encrypt that information. The public key means exactly that. The key for encrypting the information is in fact public. It is distributed to everyone. Everyone can access that key. And so this public key to encrypt the data is available to everyone to encrypt the data. On the other hand, the private key is only available to the receiver, is only available to the individual, and this private key can be used to decrypt the data. The public key cannot be used to decrypt the data. The public key can only be used to encrypt the data. Only the private key can in fact decrypt the information. And so when we want to use public key encryption, the sender will encrypt data using the receiver's public key, and the receiver will decrypt the data using their own private key. This key mechanism can also be used for making sure the right person is sending this information, and it can be used for message authentication. In this case, the sender signs the transmission with their private key, and the receiver validates that the message is from the supposed sender using the sender's public key. Monitoring activity is another way to ensure data integrity, and an audit trail analysis is performed to ensure that date and timestamps for all transactions are valid. In conclusion, data integrity is essential for maintaining good quality data, and good quality data subsequently makes for quality decision making. Many actions need to be taken to ensure high levels of data integrity, including protecting the existence of data through the use of firewalls and backup mechanisms,